Right, so now we have a function g, and this function is defined to be the integral from 1 to x. So the input variable for g actually goes right there of this function of t, right? So notice that t is the variable of integration, right? The way that you'd figure that out is you take e to the 5t squared minus 4t, you figure out what's the antiderivative of that, and then you're plugging in x and 1, right? So when you do the antiderivative and you plug in the bounds, the t goes away, right? So the fact that that's a t is not important. That could easily well be, this could easily well be w, and it would have the same meaning, because that's just kind of the dummy variable of integration. That doesn't actually stay a variable, right? That disappears as when you do the integral. The actual variable here is the x, right? Is the upper bound. So this function is simply changing the upper bound on this integral. Now, the question they're asking is, what is g prime? What is g prime? So the trick to this is the fundamental theorem of calculus, right? The fundamental theorem of calculus is the fact that integrals and derivatives are opposites of each other. If you do the integral and then you take the derivative, you get back to where you started. And if you do the derivative and then you do the integral, you get back to where you started. More or less. There's a slight asterisk on that, but more or less. So you can state the fundamental theorem of calculus in another way if you prefer, but that's pretty much, that's the meat of it, basically. So g prime, right? So what's the derivative of this? Well, if you're super comfortable with the fundamental theorem of calculus, you might already know the answer. You just say, well, look, we have this function on the inside. We're doing the integral of that with x as the upper bound. And so if you do the derivative of that, well, that's just going to cancel with the integral. And so it's just going to be that function that you started with. It's just going to be that function on the inside, which I'll use the letter x for it since that's the letter we're using for the input variable. But as always, the letter you're using is not important, right? It's some function on the inside. We were taking the integral of that, but then we undid the integral because we took the derivative, right? That's the idea. Now, if you're not that comfortable with the fundamental theorem of calculus, let's talk about that in a little bit more depth. Right, the way that we usually do an integral, when you have, like, say, the integral of some, what should I call? I don't want to use the letter f because we're using that. Well, I guess we weren't actually. Yeah, so the integral of some function, right? You first have to figure out, okay, I need to come up with an antiderivative for that function. And once you come up with that antiderivative, once you figure out that antiderivative, then you are plugging in those two bounds, right? So what we're looking at is the integral of this function. Do they have bounds on it? Oh yeah, of course it did. It was from 1 to x. Of this function, but it was e to the 5t squared minus 4t dt. So you might think that what we got to do then is figure out what is the antiderivative of that, right? What function has to what function is that which, when you take the derivative, you get e to the 5t squared minus 4t? Well, that's a pretty hard question. And, well, I'll just leave it at that. It's a pretty hard question. So here's the thing, though, is you don't actually have to answer it. Let's just call it something temporarily. So I'll just call it capital F. So capital F is the antiderivative of that function over there. Now I don't know what it is. I don't know what it is, but I'm just saying that function exists, and it has the property that when you take the derivative of that is that, right? So I'm defining this capital F to be exactly what we need, the antiderivative of this function, which I'm not going to bother to figure out. I'm just going to call it capital F. Well, watch this. Then I can plug in the bounds, right? Okay? So it turns out that that's what g is. G is equal to that integral, which is equal to that, capital F of x minus capital F of 1. Okay? Sure. So that means then that g prime, right, if g is equal to that, then g prime is going to be the derivative of that. So this is f prime of x, and then f of 1, I don't know what that is, but it's just a number, right? It's just our mystery function, which I know is just a function that turns numbers into numbers, and you're plugging in a number 1, so it's turning that into some other number. I don't know, I don't care, because when you take the derivative, it's 0. So that goes away. So the point is, g prime is just f prime, and f prime is what? It's our function. Right, so the whole idea is we just said, the antiderivative can be whatever it is. I won't even bother to figure it out, because later on we're going to end up taking the derivative, and so it just turns out to be that. So there you go. And so you can see, because the upper bound was our variable x, and the lower bound was just a number, that it turned out to just literally be the derivative of that antiderivative of x. And so it just works out to be the exact original function that we started with, according to the fundamental theorem of calculus anyway, which is that to do the integral, you need to take the antiderivative, and then we needed to take the derivative. So boom, those just cancel out. Easy peasy. All right, so there you have it. It turns out that g prime is that exact inner function. Whoops, using the letter x. You can use whatever letter you want, but just make sure that they all match up, right? Make sure that your variables match up. Okay, next one.